Okay, so this is going to be question 1. So basically was make sure that you read the question first and think about some of the information that's been given to you in here. So this bit's just scene setting. In this ride we've got an electrical conductor connected to the ceiling which has a DC voltage of 70 volts. So this bit is going to be important somewhere in the question. We've also got the fact that the ceiling is 2.3 meters above the floor. So again, this could be important somewhere in the question. So the first thing asked is to draw the shape of the electric field between the ceiling and the floor. So when you're asked to draw the shape, obviously the shape is important, but also the direction as well. So make sure that your lines between here are nice and parallel, evenly spaced. Obviously, ideally, if you're doing this in a test or an exam situation, you're going to be hopefully using a ruler, direction arrows on there, and we should also have the curved lines at the end. So your parallel evenly spaced lines here will get you an achieved, curly ends on it will get you up to merit as long as you've got your direction correct. So you're told here you've got plus 70, so that's going to make this plate positive, that's going to make this plate essentially the negative plate down here. So remember that your electric field lines always show you the direction that a positive charge would be pushed. So if you had a positive charge in here, obviously it's going to get attracted towards the negative and pushed away from the positive plate. So your direction arrow should be top to bottom for this question. The next part says show that the electric field strength is 30 volts per meter. This is a show question, so the marks are going to come from your working only, okay, because obviously you're given the answer. So here again, working as is always is important. So electric field strength, hopefully we know that that symbol is E. And if we look on our formula sheet, we'll see that one of the equations with E in is V over D. And we'd said earlier that V and D were possibly going to be important a little bit down the line. And so if we put those values in, you do indeed get 30.4, and if we're rounding that to two significant figures, that's 30 volts to two significant figures. And units on there. It is only a show question, so it's just going to be achieved. Part C says a speck of dust has become charged, and it tells us the charge. And very nicely here, they've told you the prefix values here, and it floats 1.2 meters above the floor. And they want us to explain whether the charge must be positive or negative to remain suspended in the air. So the first thing to think about here is how and why it's going to be suspended. So think about the forces involved. So as with a lot of things, if we have our speck of dust here, there's going to be forces involved here. We're going to have F gravity downwards, and we need some force to counteract that. And here, because we're in an electric field, that's going to be the electric force that we've got here. So if we want this to be suspended in the air, we know this force is going to have to counteract this force. So Fe, or F electric, must be equal and opposite to Fg for it to remain suspended. So as Fg is acting downwards, the electric force must act upwards. Okay. So if we want the electric force to act upwards, we've got to think, well, what charge would it have to be if it's going to be pushed upwards? Now we already said up here when we were talking about which direction this was in, a positive charge in here would be pushed downwards because our electric field tells us the direction a positive charge would travel in this electric field. So if we want our charge to be pushed upwards, it would have to be a negative charge. So to be pushed upwards or have a force upwards, we would need to have a negative charge. So here, this question was an E question. You got A for just stating it needed to be a negative charge. If you talked about both forces in some form or another, that got you up to the merit level. And if you'd explained it in terms of them being equal and opposite, and also then what direction your electric force would have to be, and how that would influence whether your charge has got to be positive or negative, that would have obviously got you up to the excellence level. So turning over the page on that question, it says calculate the electrostatic force acting on this dust particle. So again, this is just a case of looking through your formula sheet to see which formula is going to give you that value. So we've got F equals EQ. So we know that the field strength was 30, we were told that in the previous question. And we were also, very kindly with its prefixes, told the charge that we had involved. So, oh, whoops, sorry. If you put that into a calculator, that is what you get when we tidy it up. And because it's a force, units should be newtons. It's straightforward putting numbers into an equation, so it is only an achieved question for that one. Part E, explain how the magnitude of the force changes as the dust particle moves down towards the floor. Yeah, a couple of ways I guess you could have talked about this, but really the force is going to have no change on it. And the easiest way to explain that is because we know the field is uniform. And if the field is uniform, then the force must be the same. Because the field strength is the same everywhere. So if the field strength is the same everywhere and the force is given by E equals Q, so E is constant and the charge itself hasn't changed, so Q is also constant. So if both those things are constant, force must also be constant. So that was a merit question, and actually if you thought about it, a pretty straightforward, I think, merit question. Obviously you'd flesh that out with a little bit of detail, but I'm just trying to make this video not take too long with the explanations. Part F, I think you kind of talked around this, most of you, but not quite with enough detail. So the ride supervisor was able to step on the electrified floor while it's operating, explain why he doesn't get an electric shock. Yeah, try not to use your general knowledge and talk about insulated shoes and all that kind of things. We need to stick to the physics here. So we know the floor is at 0 voltage, and that's one really important thing to mention, that you've actually picked up that idea. We also know that current, when it flows, it always flows from areas of high potential, high electric potential, to low potential. And when we're talking about this, what that really means is that it always flows from high to low voltage. Okay. Sometimes you'll see in books it called PD, potential difference, so voltage is the same as potential difference. So really the key to this was that both his feet are on the floor, so both feet are at 0 voltage. So if they are both at the same voltage, there is no change from high to low potential here. So if at the same voltage, no current flows and he doesn't get an electric shock. So the really important thing here is about his feet both being at 0, and that's why we get no electric shock. So that's question 1.